Welcome to this presentation sponsored by the Deep Foundations Institute. The DFI is organized to serve as a primary means through which members of the Institute may participate in improvement of the planning, design, and construction aspects of deep foundations and deep excavations. This presentation was developed by the Helical Piles and Tieback Committee of the DFI. The title of the presentation is Introduction to Helical Piles and Helical Anchors. The purpose of this presentation is to provide educators and students with information on the evolution of deep foundation systems known as helical piles, helical anchors, and helical tiebacks, dating back to the product's invention in the early 19th century. Today, helical piles, also known as screw piles, are used in many countries around the world. Helical anchors and helical tiebacks have been known by other names as indicated on this slide. The most commonly used name in Canada, Australia, New Zealand, and Europe is screw pile or screw anchor. The term helical foundation is generally used to define an entire foundation in which helical piles or helical anchors are the primary deep foundation element. Helical piles, helical anchors, and helical tiebacks are pre-manufactured deep foundations. This slide details the component parts that comprise these products. Major components are extension section, lead section, and helices. The drawing on the right shows a typical helical plate. The pitch is defined as the vertical distance between the leading edge and trailing edge of the helix plate. The helix plate will move downward into the soil at the rate of 1 pitch per revolution. Helical piles, anchors, and tiebacks are installed using a torque motor attached to a source of hydraulic pressure. The installation process produces no soil spoils, there is no vibration involved, and they can be installed in nearly any weather conditions. Four-helix helical pile about to be installed with a track hoe excavator. Note torque indicating device located just below the hydraulic torque motor. Helical piles are typically installed with machine-mounted hydraulic torque motors. The machines can be front-end skid steer loaders, mini excavators, rubber-tired backhoes, and large track hoe excavators. Helical piles can also be installed with portable hydraulic torque motors, which keep mobilization costs down and minimize site disturbance. Portable installation equipment makes it possible to install helical piles in very tight access locations. Helical piles come in many sizes and shaft types. Shafts range from slender square shafts to large diameter pipe shafts. The majority of helical piles use shaft diameters of 3 1/2 inches or less. Helical piles can be single or multi-helix configuration. The helix diameters on multi-helix piles usually taper from smaller to larger from the tip of the pile. The helix plates can also be the same diameter. Grout is sometimes used both on the outside and inside of the pile shaft. This slide lists several of the advantages available with helical piles. Some of the major advantages include low mobilization cost due to small and inexpensive installation equipment, low noise and minimal vibrations, year-round installation in any weather. This slide lists several of the possible disadvantages of helical piles. Major ones are unable to penetrate competent bedrock without pre-drilling, potential refusal in heavy cobble and boulders, installation difficult in trash fill with concrete and other building material debris. Historical development. An Englishman, Alexander Mitchell, is recognized as the inventor of the screw pile. The first recorded use of screw piles was for boat moorings and then for lighthouse structures along the Thames River. Mitchell traveled extensively as a consultant to the United States and to other English-speaking countries. The first recorded use of screw piles in the United States was in 1843. Today, helical piles are used worldwide. During the 19th century, screw piles were used as deep foundations for a variety of structures, including lighthouses, buildings, railroad bridge piers, seaside piers, and platforms. The drawing on this slide is the Maplin Sands Lighthouse in England. This slide shows a typical lighthouse structure supported on helical piles. The picture on the right is a spud barge with a large capstan used to install the screw pile. Mitchell authored several technical papers. This slide shows an excerpt from one of his papers published in 1848. Mitchell cites the three basic design parameters required for helical piles: minimum depth, soil strength, and bearing area of the helix. Helical or screw piles entered a quiet period during the first half of the 20th century, primarily due to development of other deep foundation methods and advances in pile driving installation equipment. After World War II, helical piles made a comeback with the development of high-capacity hydraulic torque motors, which greatly improved installation, time, and cost. Today, advances in geometry have resulted in more efficient helical pile designs. They are used for foundation repair, underpinning, new construction foundations, earth retention, tiebacks and helical soil nails, tie-downs, guy anchors, seismic retrofit, and many other applications. Research continues into behavior as related to capacity and serviceability. Helical piles continue to provide cost-effective, deep foundations in our modern world. The shaft sizes range from 1 1/2 inch square bar to 12-inch diameter and larger pipe shafts. Helical plate diameters range from 8 inches to well over 24 inches. Lengths vary, but can range from 7 feet deep to well over 100 feet long. Theory and design. Many design variables must be considered for helical piles. However, the basic engineering principles used are similar to those considerations made for other deep foundations. Theoretical capacity models depend on accurate soil properties, tests, and experience. Theoretical models usually depend on soil strength correlations, estimates, and disturbance factors related to the means and method of helical pile installation. A common theoretical capacity model used with helical piles is the individual bearing plate model. It assumes each helix plate acts as an individual bearing element in soil. The total capacity is equal to the sum of the capacities of each individual helix plate. Bearing capacity is calculated using the Terzaghi general bearing capacity equation. The designer must make use of the appropriate soil parameter, either effective stress parameters for long-term slow loading in sands and clays, or total stress parameters in rapid loading of saturated clays. Helical piles, anchors, and tiebacks are manufactured in many different sizes with corresponding compression and/or tension capacities. It is precisely this wide spectrum of products and capacities that makes these products such viable deep foundation solutions for many different applications. Installation torque, resistance to helical pile penetration, can be used to estimate the ultimate capacity of helical piles. Torque correlations have been empirically established based on load tests done over many years in many soil types. This slide shows the relationship between the installation torque and the ultimate capacity of a helical pile. This relationship, that is, correlation, has been termed K sub T. The torque correlation factor K sub T is inversely related to the shaft size and follows the trend that as the helical pile shaft increases, the K sub T factor decreases. This slide gives the main factors that affect K sub T. Soil conditions and shaft size are the two primary factors. Researchers Robert Hoyt and Dr. Samuel Clements published Uplift Capacity of Helical Anchors in Soil in 1989. It is considered a landmark paper on torque correlation for helical piles. In this paper, Hoyt and Clements proposed several K sub T factors which have become commonly used in the industry. The most common factor of safety used for most permanent helical pile applications is a factor of safety of 2. Applications where extensive testing is required allow for lower factors of safety. Research shows that buckling is a practical concern only in the softest soils. The industry recommended standard for minimum spacing for helical anchors, tension applications, is 4 times the diameter of the largest helix bearing plate, with 3 feet being the absolute minimum spacing. This slide shows recommended minimum depths. The lateral capacity of helical piles is calculated the same way as with other types of deep foundations. Lateral capacity can also be mobilized via other foundation elements, such as the grade beam and optional lateral tieback anchors. Helical piles can be installed at a batter. The orientation of the piles then allows them to resist lateral loads. Underground corrosion needs to be evaluated for helical piles, as it should be for all deep foundation systems. Disturbed, unsaturated soils near the surface are generally more corrosive than saturated, undisturbed soils deeper below the surface. Near the surface, it is common to use protective coatings, such as hot dip galvanizing, epoxy, and concrete. This slide shows the AC 358 corrosion protection requirement. The following list are factors that affect the installability and load capacity and performance of helical piles. Several of the most important are proper sizing of helical bearing plates for the bearing and pull-out capacity of the soil, minimum final installation torque, and mechanical capacity of pile and anchor components. This slide gives brief definitions of the three most common types of specifications used for the installation and use of helical piles. The most common and most often used is the performance specification. Applications. Tieback wall in Omaha, Nebraska. Helical tieback anchors are used for earth retention. Tieback wall at O'Hare Airport in Chicago. Helical tieback anchors installed in very cold weather conditions. TVA 500 kilovolt substation near Memphis, Tennessee. Helical piles used to support large dead-end structures and transformer pads. Telecommunication tower guy anchorage with multiple guys and multiple anchors. Helical anchors are widely used to counteract buoyancy issues for a variety of structures that are below the water table, such as buried gas transmission pipelines, as shown in the photo above, and empty to nearly empty underground storage tanks in high groundwater conditions. They have also been used to anchor plastic septic tanks in situations where the tank, which weighs next to nothing, becomes close to empty and the water table is high and the ground cover over the tank is only 1 to 2 feet. Helical piles installed to support structural slab inside existing building. Helical piles being installed to support single-family and multifamily structures, including structural slabs in regions with heaving soils. Helical pile installations are vibration-free, making them a viable solution for projects with close proximity to existing structures. Large diameter helical piles being installed at an oil refinery. Large diameter piles being installed at a batter angle for above-grade pipeline support. Helical piles being installed to replace failing wood pilings and cross members for an above-grade pipeline. Helical piles being installed to support a large grain silo. large diameter helical piles being installed using a drill rig to support a multi-story parking garage. Helical piles being installed for single-family houses. Walkways for wetlands. Helical piles supported walkways to provide public access to wetlands and wildlife areas. These piles provide minimum disturbance during installation. Nature walks. Helical piles supported walkways to provide public access to wetlands and wildlife areas. Again, these piles can be installed with really no damage to the environment. Helical piles being installed to support an addition to a mountain cabin. Helical piles are used to support decks, gazebos, and other above-grade structures. Helical piles are used extensively for underpinning existing foundations that have experienced differential settlement. Helical piles being installed to support the addition of an MRI system at an existing medical facility. This slide provides a perspective of the many applications for which helical pile, helical anchors, and helical tiebacks are viable solutions. Case history. Ford Field in Detroit. Helical tieback anchors used to construct a temporary retaining wall during construction of the stadium. Elevation view of typical wall face. Section view of typical wall face. Load deflection plot of extended creep test on helical tieback anchors for the Ford Field project. Continued study. There are many industry organizations that support information on helical foundations. The DFI, Deep Foundations Institute, the ADSC, International Association of Foundation Drilling, and other many organizations provide information on helical foundations. Helical Pile World is a website that often contains useful information for helical installations. This slide lists trade shows and seminars. This slide lists books. This slide is the conclusion to this presentation.